So my name is Shubham Rai, and I am a PhD research scholar in Department of Applied Mechanics, IIT Delhi. So today we are going to solve some problems related to week 10 lectures. Okay. So in week 10, you would have studied about shear centers and theory of bending of beams. So we will take some numericals related to that only. So let me just start. So first numerical is a flat steel bar which is 1 inch wide by 0.25 inch thick and 40 inch long is bent by couples couples applied at the ends so that the midpoint deflection is 1 inch. So only couples have been applied. So this is a case of pure bending. There are no transverse uh, point loads or uniformly distributed loads are applied. So only couples have been applied. Also, couples are not varying with respect to length of the beam. It's a case of pure bending. So okay, so what you have to do is you have to compute the stress in the bar and the magnitude of the applied couples. Okay. Now this is the kind of inverse problem. So generally in problems that you deal generally, so in those problems you have material properties and you have given force and you find the displacement. It's not inverse actually, but I mean only thing is here you have been given with deflection and you have to find the force. Generally you have the force and you find deflection. Here reverse thing you have to do. So material properties and deflection is given to you. You have to find moments or forces. Okay. So you have to use material property E is equal to 200 GPa. So we will use theory of pure bending here. So let me just start the solution. If I draw the bar, so bar will look something like this. And let's say this is the center about which it is bending. So after bending, the shape of the bar will be something like this. Okay, let's say this is the shape after bending. And so this is the total theta that it has covered. And if I draw the cross section of the bar, so information about cross section is given in the question. Let's say this is the cross section of the bar. So So the width of the bar is 1 inch. So this is 1 inch, and thickness is 1 to 5 inch, means 1 by 4 inch, right? And so this will be the radius of curvature. So I'm taking it as rho. So rho is the radius of curvature after bending, and this will be the, let's say, couples that will be acting, that has been applied. And we have to find the value of these couples and the stress on the bar, right? So how do we find it? And also you have been given that central deflection here. This central deflection is given to you, which is, so this is 1 inch, right? So how will you find? Can you guess? In this case, what we will do is we will try to find out this radius of curvature rho. And once we have this radius of curvature, we can apply the formula of pure bending. So that formula of pure bending relates radius of curvature, bending moment, I mean this applied moment, okay, and the stresses also. So from there, firstly we can find the applied moment, and then after that we can find stresses, right? So how will you find radius of curvature? Because from the geometry we can find it out. So it's, since this is a case of small deflection, we are dealing with small deflection problems. So we can say that, so this total length is 14, so this will be 20 inch, and this will also be 20 inch. And if you focus on this triangle here, okay, in this triangle, let's say this is the total length. So in this triangle, if you apply Pythagoras theorem, what will you get? Let's do that. So I'm calling this deflection as delta. So delta is given to you as 1 inch, right? And rho do not know. Rho you have to find. Okay. So if we apply Pythagoras theorem in this triangle, so the perpendicular direction will be, this will be the radius, right? And this is delta. So this side will be rho minus delta. So you will get here rho minus delta to the whole square, plus base is 20. So this is 20 square, and that will be equal to radius square, right? So if you solve this equation, only unknown here is rho, because delta is already given to you, that is 1 inch. So um, so you will get rho minus 1 to the whole square minus rho square, so that will be equal to minus 400, right? And if you do so, minus rho square will get cancelled. So finally, um, what should you get? So you will get 1 minus 2 rho is equal to minus 400, right? So rho finally, what you will get? 400 by 2. 401 by 2. That will be 200.5. This and units will be inches, right? So you have found out the radius, and once you have the radius, you can find out the moment, applied moment, because you have this formula m by I is equal to E by R, right? This is the bending formula that we have. This is uh formula that we have derived for pure bending, but it's also valid for non-uniform bending. Only thing is there, this R will not correspond to the radius of the whole beam, rather it will be the radius of curvature at a particular point. Anyway, so for finding M will be E, which is given to you, which is 200 times I. What will be I? I will be 1 by 12 into, what is the width? This is 1 inch, and divided by height to the cube, 1 by 12 bh cube. So that is I and divide by R. R is 200.5, right? So you should solve this. What will you get? So also you need to convert this into, so you cannot put here directly 200. I'm just putting E here. So you have to put E in pounds per inch square instead of Newton per meter square. Okay. So obviously that was in gigapascal, so you could put 200 in 10 power 9, but you have to put in pounds per inch square. So 1 pound per inch square. So that is equal to 0.00689476 Newton per mm square. Okay. So from here you can convert Newton per meter square into pounds per inch square from this formula. And if you put all the values, finally you should get m is equal to 188.3 pound inch. Okay. So that's what you should get. Now you need to find out the stresses. How will you find out? So stress, you know that sigma, so that will be next direction. So let's say I'm calling it sigma x by sigma xx because that is a normal stress. So sigma xx by y is equal to minus E by R, right? That's what we had derived. So from here you can get sigma xx is equal to minus EY by R. So finally you can just put the values and you should get this in pound per inch square. Okay. And y you can, so this will be minus E times y should be, so we will be interested in maximum stress. So this y should be maximum distance from the neutral axis. Neutral axis will be at the will coincide with centroid here, which is at center line of this bar. So it will be y should be thickness divided by 2. Thickness is how much? 1 by 4 inch. The thickness divided by 2 will be 1 by 8 inch. And divided by 1 by rho divided by r. So which is 200.5. So you can just find out what should be the maximum stress. Okay. Are there any questions or doubts in this question? So, okay, if there are no doubts, let me move ahead. So let me write problem number 2. Problem second. So let me first write down the question. In a laboratory test, for beam loaded by end couples the longitudinal fibers at layer AB in the figure below are found to increase 16 to 10 to the power minus 3 mm. I'll draw the figure, don't worry. Whereas those at CD, I'll show where this AB and CD will be. So these decrease 100 transform as 3 mm. In the 200 mm. The initial length was 200 mm. Okay. So 200 mm gauge length. So you have to use using E is equal to 70 GPa. What you have to do is you have to determine the flexural stress. You have to determine the flexural stress in the top and bottom fibers. So please read the question once. So in a laboratory test of a beam loaded by end couples, the longitudinal fibers at layer AB in the figure below are found to increase by 16 newtons per minus 3 mm, whereas those at CD decrease by 100 newtons per minus 3 mm in the 200 mm gauge length. Using Young's modulus of elasticity as 70 GPa gigapascal, determine the flexural stress in the top and bottom fibers. So what you need to do is, so let me first draw the diagram. So it's something like this. So different section. Okay, so let's say this is the beam. So there are fibers. So let's say one fiber is here. This is fiber AB and this is fiber CD. So it parallelly so should come here. Should come. Okay. So this gauge length is 200 mm and this distance here is 30 mm, whereas this distance is 120 mm and this distance is 75 mm, right? And this is fiber AB, which was getting in tension, and this is fiber CD, which is getting compressed. So you have to find flexural stress in AB and CD, or let's say in the top and bottom fibers. That also you can find. So how will you do that? Please think about it. So you can start by locating the neutral axis. Let's say neutral axis is at some place. From there, let's assume that these fibers at a distance of at these fibers are at a vertical distance. So we can assume that the neutral axis is at distance x from fiber AB, has a vertical distance x from fiber AB, and correspondingly we can define all other distances. And From there we can proceed. Okay. So about neutral axis, on neutral axis there will be zero strain. Right? So let me just try to solve it. So if you draw the diagram again, see this is the beginning. So I have to, I don't know where I mean what is the exact length, but we know the gauge length. Gauge length means the length after gripping the specimen, after I mean the length that is actually important in which the bending is going to happen. Okay, so let's say this is fiber AB. Fiber CD. I'm just showing fiber. Let's assume that neutral axis is lying somewhere here. Okay. And I'm just extending these lines. It will be here. It will be here. And top and bottom also I'm extending. So fiber will be here. Fiber will be here. So I let's assume that from this is A, this is B, and this is C, this is D. So let's assume that the neutral axis is at distance x from, let me write down these distances again. So this is 30 mm, and this total distance is 120 mm. This is 75 mm. And I'm assuming that the neutral axis is at a distance x from fiber AB. So this distance is x here. If this is x, this will be x plus 30. And if this is x plus 30, so total length is how much? So 120 plus 30 is 150 plus 75. So that is 225. 225 minus 30. So that will be 195 and minus x. So this distance will be 195 minus x, right? And finally, I would also like to find this distance here. So this distance, what will be that? So that is nothing but 120 minus x. And if you try to draw the strains, so strain here is, let me just draw strain here is positive. First draw a straight line. Let's say straight line, strain here, and AB strain is positive, and in CD strain is negative, and it's a large quantity. Finally, the strain will be something like this, right? So this is the graph of the strain, and here it is given to you that this delta tau, that is 16 to 10 to minus 3 mm, and Here you have delta bottom, that is 100 into 10 to the minus 3 arc, right? And this is obviously neutral axis. Okay. Now, how will you find? So you know that epsilon xx. What is the formula of epsilon xx? That is minus y by r, right? We derived this formula in the class. So epsilon xx is minus y by r, where um, y is distance of the point from neutral axis where you want to find out the strain. So this radius of curvature obviously is constant here because it's a case of pure bending. Okay. So this radius of curvature is constant. So we can say that this epsilon xx over, or we can say that y minus y divided by epsilon xx. That is also constant. So this must also be constant. Why? Because if you take y here, so y by epsilon xx, and this will be equal to r, and r is a constant, so that's why y by epsilon xx will also be constant. So now if you equate the ratio at these 2 points, at this point here and this point here, of y divided by epsilon xx, so let's see what happens. So what is the value of y here? So don't get confused with y and x. Actually, y is, we have taken x is the distance of the neutral axis from this top fiber, and y is distance of any point from the neutral axis. Both are vertical distances only. These are not, x is not horizontal distance here in this question. Okay, so let me equate this quantity. So this is a constant. This will be a constant quantity across the section of the beam. So let me equate it for this point here, B, and point D. So I mean, for the top fiber and for the bottom fiber. So the top fiber, what is the distance of top fiber? The distance of top fiber is x, right? And what will be the strain? We do not know the strain. So let's say, let's call it as strain in AB. I mean, we know the strain. So let's call it as strain in AB. And from here, we can find the value of x, that is the position of neutral axis from the top fiber. And for the bottom fiber, what will be this? So the distance of bottom fiber will be minus of 120 minus x, right? And then divide by epsilon CD. So this is the strain in the bottom fiber. Now, if you solve this equation, what will you get? So finally, you are getting x epsilon AB is 16 to 10 to minus 3 divided by 200, because this is change in length over original length. And here you'll get x minus 120 because there is a minus sign. And here there is a compressive strain. So this will get minus 100 into 10 to minus 3 divided by 200. Right. So this will be the strain in top and bottom fiber because initial length is 200. Now from there, from here, this equation, you can calculate the value of x. So if you calculate, so you'll get x is equal to 0.6 times 120 minus x, right? And if you solve finally, you will get x is equal to 45. So x is 45 mm. So what we have done initially is we have analyzed that if this is the formula of strain and if this is a case of pure bending, so r is going to be constant. That's why this ratio of epsilon xx or y divided by epsilon xx will be constant. So that's why we have equated this ratio for the fiber AB and fiber CD. And from here, we have found out the value of x, that is the distance of the neutral axis from the top fiber. Now we have the distance of the neutral axis, so x is 45 mm. So neutral axis is at distance of 45 mm from the top fiber. Okay. Once we have this, we can find the strain at any point, right? Um, so let's say we want to find the strain in this topmost fiber, right? That is at a distance of x plus 30 from the neutral axis, right? If we do that, so now let me just write. So for top fiber, and by top fiber I mean this topmost fiber here. AB was top fiber, but it was not topmost. Somewhere, I mean, it is compared to CD, it is at top. And compared to AB, CD is at bottom. The topmost fiber is this one, what I mean, which is at a distance of x plus 30 from the neutral axis. We know the value of x. So now if we write this equation for top fiber, so that will be x over epsilon AB. So that you have to write this equation at 2 points. So I'm writing for AB because for AB we know the strain of AB and we know the value of x also, which is, I mean, x is the distance of AB from the neutral axis. Now for the second point will be the topmost fiber, which is at a distance of x plus 30. So which is x plus 30, and here the strain will be epsilon topmost. I'm just writing top. Okay. So if you solve that, so x will be 45 over epsilon AB will be 16 to 10 to the minus 3 divided by 200. And this is x plus 30. And epsilon top x is, I mean, 45 plus 30. And epsilon top. So from here you can find epsilon top. So from here, epsilon value of epsilon top that you will get will be 5 into 10 to the minus 4. We can calculate also if you want me to calculate. So let's do that. So epsilon top finally will be 7. So this will be 75 divided by 45. And this 16 to 10 to the minus 3 will come here and 200 will come here. So finally, if we solve, 0 will get cancelled with this 0. And what else you can cancel? So, so 15, 3 are 45, 15, 5 is 75. 5 and 5, 5, 4 are 20, right? Yeah. And 6 and 6, 16 and 12. So you're getting 1 by 6. Oh, sorry. So 525, 5, 4 are 20. Yes, 3 1 is 8. You'll get 2 here. 3 by 6. Finally, you'll get 2 here. So you are getting actually, am I missing something? Yeah, don't missing anything. So you're getting 1 by 2 into 10 to the minus 3. So which is nothing but 0.5 into 10 to the minus 3, which is 5 into 10 to the minus 4. So finally you will get this. So this will be the strain in top fiber, and once you know the strain in top fiber, you can find the bending stress in top fiber. So that will be flexural stress in the top fiber. That's what we need to find out. This will be E into, so sigma I'm studying, E into epsilon top. This is sigma top. E is how much? E is 200 into 10 to the power minus. It is 70 GP. So okay. 70 into 10 to the power 9 GPA. So it will be Newton per meter square. So and this will be 5 into 10 to the minus 4, right? So finally, what will you get? 35 into 10 to the power 6, I think. Yep. Finally, you will get 35 MPa. 25 megapascal stress in the top fiber. Similarly, you have to find in bottommost fiber. So for bottommost fiber, you equate this ratio for the bottom fiber and for the CD fiber CD and this bottommost fiber. So if you do that, let me just write, use a different color. for bottom fiber. So x divided by epsilon. You can use AB also because CD has negative sign. So we want to avoid that. So I'm just using AB. So x divided by AB because x is also very easy because CD is at a distance of 195 minus x. So the calculation we would involve, sorry, CD is at a distance of 120 minus x and AB is at a distance of x. So it's very easy to go with AB. So we'll take this fiber AB and this bottommost fiber. So if we do that, so the fiber AB is at a distance x from the neutral axis. And this bottommost fiber is at a distance of 195 minus x from the neutral axis. So we'll go with x and 195 minus x. So x divided by epsilon AB should be equal to um, minus of 195 minus x because it is 195 minus x is positive quantity, but it is at below the neutral axis, so that's why minus n will be there because y coordinate will be minus and divide, and this will be epsilon bottommost. The only unknown here is epsilon bottom because x is 45, epsilon AB is 16 to 10 power minus 3 over 200, and this is x minus 195. Just 45 minus 195 divided by epsilon bottom. If you solve for epsilon bottom, what will you get? So this will be 45 minus 195. So how much it will be? I think it will be 150. Yeah, this will be 150 and divided by 45 and multiplied by 16 to 10 to the minus 3. This will be minus because, and then divide by 2, right? So again, you can take 15, 115, 45 and 10. So you can use 15. You can cancel this 15 3 or 45 and 15 times 10 is 150. And then you can just cancel these two quantities, these two ratios, and then 3 minus 6. So also get cancelled. So finally, we are getting minus of 10 to the minus 3. So this is strain at the bottom. So once you have strain at the bottom, so you can calculate stress at the bottom. Stress at the bottom, that will be E into strain at the bottom. E is again 70 GP, so 70 into 10 power 9 into minus of 10 power minus 3. So finally you are getting 70 minus of 70 MP megapascal. Okay, this is the final answer. One part of final answer, this one. The first part we have already given here. You see how we have solved this question. And also one thing to observe is this stress is less, whereas this bottom stress is more. The reason is your neutral axis is above central point, right? So you get more strain in the bottom fiber. That's why the stress is also more. You get less strain in the topmost fiber, so that's why stress is also less. Okay? Because neutral axis is above the central line. Okay, so is there any doubt in this question? So only concept involved was you have to look at this formula and you have to realize that in case of pure bending, this ratio y by epsilon xx is going to be constant, which is equal to radius of curvature of the whole beam. And that is for pure bending, radius of curvature for the whole beam will be same. Only you are applying the moments. That's why it's a case of pure bending. So here it has been given that in a laboratory test of a beam loaded by end couples. So you are only applying end couples. That's why it's a case of pure bending. So let me drink some water, then we will move to problem number 3. Well, I also charge my pen. Just wait, I'll be back in a minute. Let me see how much it is charged. Make it 11%. So let it go to at least 20%. Okay, so let me write down next question. The next question is related to the concept of shear center. So let me just write down the concept of shear center. So you would have studied shear center. What is shear center? So shear center is the point in the cross-sectional plane of a beam or any cross-sectional plane. Point in the cross-sectional plane relative to which the net torque due to shear stress distribution vanishes. Right? Also, we can say that so the point in the cross-sectional plane related to which the net torque due to shear stress distribution vanishes. So there will not be any torque due to shear stress distribution about this shear center. Now there's one more note here. The shear center always lie on always lies on the line of symmetry of the cross section. So if you have a symmetrical section, so it will always lie on the line of symmetry of the cross-section. Okay, so let me write down the question. Question related to shear center is, so what you have to do is you have to think for beam whose cross-section has the shape of a thin annular disk. But cut is there along a radial line on x-axis. Okay, so you have a beam whose cross-section has the shape of a thin annular disk, but a cut is there. Small cut is there along a radial line on x-axis. Sorry, so it will be z-axis as you can imagine. So yeah, as per the conventions taken in lectures, so this will be z-axis. I draw the figure as well, don't worry. Question is, how will the shear stress distribution be in the cross section? So how will the shear stress distribution be in the cross section? That's the one point that you have to tell. So also you have to tell, will such a beam undergoes just bending, or it can also twist? So you have to tell, firstly, I mean, you have to find the shear center of this beam actually. So if you know the center, and then you will also know that if you apply any load passing through the shear center, so beam is only going to bend, because about shear center there will not be any torque due to shear stress distribution that will be acting on the beam. So since no torque will be acting, there will not be twisting. There will only be bending. So if you apply load passing through the shear center, so torque of that load also will be zero, because it is passing through the shear center. It does not have any distance from the shear center. Whereas if you apply a eccentric load, which is at some distance from the shear center, so it will introduce some torque. So that will lead to twisting of the beam. Anyway, so firstly, let me draw the diagram. So let me draw this first circle and the second circle. maybe. Okay, it's fine. Now let's join these two ones. Let's say there is a cut here. I mean, the cut is so small that practically I'm drawing it, but it will be very small. So you can just erase these areas. Okay. So this will be the cut, yes. And this will be the axis. And so this will be the line of symmetry, you can see. And the shear stress distribution, let's say, will start from here and go in this direction. As discussed in the lectures, it has to be, so because it is a thin cross section, it has to be like this in a particular, it will flow in a particular direction. Uh, I'm assuming that the direction of flow will be like this. And if the direction comes out to be reverse, I'll get a minus sign. Okay. So this is an angular disk and a small cut has been made. So let me just do the solution. So we'll have to find the shear center of this beam. So we know that shear center is going to lie on this line of symmetry. So we draw this figure again. So, and so okay. Just bear with me. I'm drawing the figure. Fine. That's fine. So let's say that this is the center. This is the y-axis, and this is the z-axis. So this is y-axis. This is z-axis. Okay. Let me just enlarge the z-axis. So let's say z-axis is going to here. So this is y-axis. This is z-axis. And somewhere here there is a shear center. Let's call it SC. So that is shear center. Okay. And we need to find out the shear center from this centroid. This is the centroid point O of this cross section. So this is the centroid because this width is very small. It is approaching to 0. We have just made a slit. It's a very fine cut. There's no physically there is no gap in between these 2 points. Only then only if you pull this annular disk, only then we'll be able to see the gap. Otherwise, it will be kind of touching each other. Okay, so other information given here is that this thickness of this annular disk is T. So different color. So thickness is T, and let's say that coordinate along this annular disk Let's say that this coordinate is S, right? And obviously this is line of symmetry. So how will you find the shear center? So you know that Z coordinate of shear center is given by the formula. So there is a formula for finding Z coordinate of shear center. So let me just write it down. That formula has been derived in the lectures. So you can go back to lectures and watch the derivation of this formula. I'm just writing the formula. Z coordinate of shear center is given by, so that will be delta Z, and that will be 1 over I Z Z, and then should go from 0 to 2 pi, and then R E R, because uh, multiplied by cross, it is cross product between R E R and then Q Y theta E theta. Initially it was S Q Y S E S, but our S coordinate is theta coordinate here because theta is in the peripheral direction and circumferential direction. S is also in circumferential direction, so I'm just writing theta here, right? And this was dotted with I cap. Okay, and this was from 0 to S. So but our S coordinate is theta coordinate here, and our theta is going from 0 to 2 pi. So, and what is this QY theta? So QY theta is first moment of area with respect to, so let me just define what is QY theta, then only you will understand. So QY theta, if you remember, so that was nothing but integral of y times d. So you can say that it is first moment of area with respect to z axis. Okay. And how will you find it out? So it is area integrals, and yeah, I'm just writing double integral over here. So let me just take small element. So if I take small element of this annular disk, how it will look like? And that was also equal to y bar into a, to the point you are integrating. So y bar will be the centroid of that region to the point you are integrating this area, and this area will be the total area of that to the point that your S is going. Okay. I think sometimes it is shaded area. Anyway, so let me just draw the section of this annular disk, then it will be more clear. So let me just draw this. This is some section of annular disk. Oh, yes, okay, this only. And put it here. So let's say this is some section of the annular disk, and okay. So let's say we are at 0, we are starting from 0 and we have reached up to theta. So let's say this angle is theta. And in between, let's say this angle is phi, and we are moving from phi to phi plus d phi. This angle is phi. We just enlarge, so this angle is phi, and we are moving from phi to this angle. This angle here is d phi. We are moving from phi to phi plus d phi. So let me just mention here that it is d phi. Okay, and so this will be the radius. This will be the radius of the annular disk. Sorry. If this is radius, then you can just find it out this distance here. So this distance here will be r sine phi. So this will be, because this is radius, then this distance from here to here will also be radius, and this angle is phi. So this will be r sine phi. Okay, I've written that this vertical distance. So let me draw this triangle separately. So something like that. So this is radius. This phi. So this will be r sine phi. So this is r sine phi. Um, you can easily write. What I want to do is I want to take this small cross section of the beam. So this small section of this beam. Okay, and I want to find dqy. Only then I'll be able to integrate this qy. No? If I have this dqy, integration of dqy will be qy. So, and then further qy also have to integrate. Actually, if you see here in this formula, y, since this is an annular disk, your y is constantly varying. Y coordinate is varying constantly. Okay, and your area is also a function of y coordinate. So to get qy at particular theta, you need to integrate. You cannot directly get it. That's why I just want to write the dqy for small cross section and integrate from 0 to some theta. So that such that I get qy theta. And then I integrate that qy theta and this expression from 0 to 2 pi. Okay. So let me just write what is dqy. So dqy theta. So that is the area of this. So dqi is nothing but y prime into a. So that's what I'm writing. Y prime of this section will be this r sine phi. Okay, because this is distance of the centroid of the section from the y-axis. So that will be r sine phi. And what is the area of this small section? So uh, that will be dA. So the dA is given by, so this is thickness will be t, and this distance will be r d phi. Okay, because theta is equal to arc over radius. Arc is this distance, and theta is d phi. Actually, I mean angle is d phi. So you will get this length as r d phi. So this length here is r d phi, and this thickness is t. That's it. So you'll get area. Your small area will be t times r d phi. Right. So you have got this dqy theta. So that will be r squared t sine phi d phi. So you see here that your, and why we have found out dqy theta, because we cannot find y bar directly for this annular disk. So we'll have to go with this expression. So this is your dqy. So this is essentially y dA. This one. Y, where y dA is small area of this um, small area element that we have taken, and y is this coordinate of the centroid of this area element, which is r sine phi. So now if you integrate this, you will get qy theta, and phi will go from 0 to theta. Right. So Finally, your qy theta will be r square is a constant, t is a constant, and integration of sine pi will be minus cos pi going from 0 to theta. So that will be it is cos pi minus of cos pi and going from 0 to theta. So if you evaluate it, so you'll get minus of, you will get 1 minus cos theta. You'll get minus cos theta and then minus sine, then minus cos 0. Right. Finally, you will get qy theta is r square t times 1 minus cos theta, right? So this is qy theta in your case. Now if you put in this expression, so this qy theta is in direction e theta and this r is in direction er. So er cross e theta will be, so you can imagine that this is, let's say this is er, this is er direction, er cap, and this will be here e theta cap. At any point, obviously it will change. Uh, so this is here e theta cap. So er close e theta. This is e theta cap here. So er cross e theta will give you ex, right? That will be, if you apply cross, if you apply right hand thumb rule, so you'll get ex, and that is the next direction. So and you are dotting, I mean you will get I cap actually. So and you are dotting that with I cap, so you'll get 1. So finally, you will get delta z. So that should be, let me just write it, 1 over izz integral 0 to 2 pi, and r will be as it is, and qy theta will be r square t 1 minus cos theta, and oh, here actually you should have d theta also here. Okay, just verify here, it should be d theta. Yeah, so in the formula it is ds. So now here ds s along x coordinate. Along s coordinate we have taken theta coordinate, so it will be d theta. Anyway, so now we need to find izz. How will you find? So izz we can find using this theorem that izz plus iyy. So that should be equal to ixx. So it is something perpendicular axis theorem. So and izz will be equal to iyy because this is a very, I mean the slit is very small. So there's like zero separation, almost zero separation between these two. So that's why this is symmetrical, and izz will be equal to iyy. So it will be 2 times, this will be like 2 times izz. That should be ixx. And izz will be ixx divided by 2. And ixx for so ixx will be generally second element of area is r square dA. So r is radius, and you integrate dA, so you get total area of the cylinder disk, which is 2 pi r t, right? And divide by 2, so finally you'll get pi r cube t. This is your izz. Finally, you can put all the things in this formula of delta z. So the delta z is going to be 1 over pi r cube t, and r cube t is in the numerator also. We can take it common outside integral because it is constant, and 0 to 2 pi 1 minus cos theta d theta. Okay. So you will get finally 1 over pi. There should be one more r. So one r is coming from r square is coming from qy theta, and one r is already here. Okay, actually, yeah, I got it. Actually, here it was ds. So ds is, if you see direction wise, ds is same as theta. I mean, s direction is same as theta direction. So that's why es is same as e theta. But ds will be equal to r times d theta. The distance is not same, right? The d theta is the angle, r d theta is the distance, and s is also a distance, because that's why ds will be equal to r d theta. So here you need to put one more r. Okay, there will be r4, not r cube. Okay, r4 coming here. So you will be left with one r. So we get r by pi, and then integral of. Have you got it? That it will be ds will be equal to r d theta. If you go by small amount ds, so that arc length will be equal to, so you here go by d theta, so that arc length will be equal to r d theta. Anyway, so this will be r by pi, and if you integrate, so integration of one will be theta, and integration of cosine will be sine, and both are going from 0 to 2 pi. This will, sine going from 0 to 2 pi will be 0, because if you see a sine curve, so area between sine, so that will be a whole curve, so positive area will be equal to negative area, so that will be 0, and this will be 2 pi minus 0. So essentially you're getting 2r. So your delta z is at a distance of 2r. Means your shear center is lying at a distance of positive 2r from z axis. So this distance is 2r. 2r from centroid of the section. Okay. So now once you have this distance 2r, what it means is, let's say you have this angular distance. Let me draw it very nicely. I want to be good with my drawing, but I'm not. So okay. Let's say it is fixed from here. So it's fixed from here. And say at the center you have, this is the center of the beam, and this is a distance r. Okay. This is the radius of the beam, radius of the cross section. And we know that shear center is at a distance of 2r. Okay. So if we go ahead at a distance of 2r, so let's say I let's say we build some structure so that it is at a distance of 2r. let's say this is again r. So total distance, this total distance becomes 2r. Now, if you apply any force passing through this point here at the end, this is the point at 2r. Now, if you apply any force passing through this point, so beam is going to bend, it's not going to twist. Okay. Obviously, this beam has a slit at the center, and slit will be here only, here along the z-axis only, I think, yeah, in reverse direction. Okay, so slit will be somewhere in reverse direction, so it will be somewhere here where there will be slit. And if you apply load passing through the shear center, your beam is going to bend, not twist. Okay. So it was a very interesting problem. You can revisit this problem if you have any doubt. You can um, type in the comment section of YouTube, or you can type now as well if you want to ask. Okay, let me go to the next problem. So next problem is related to, you would have studied about Euler-Bernoulli beam theory and Timoshenko beam theory. So next problem is going to be related to Euler-Bernoulli beam theory, which is valid for thin beams. So let me just do a recapitulation about Euler-Bernoulli beam theory. So in this beam theory, we assume that the central line, that the plane rotates with central line equally. Okay, I mean the plane is always, the projectional plane is always perpendicular to the central line even after deformation. So here only we have one unknown, that is the displacement of central line, and the orientation of the central plane. We need not to find that because that is perpendicular only with the central line. Just charge my pen a bit. So do you remember what was the bending formula for this Euler-Bernoulli beam theory? I will just write this. Wait a minute. The pen is getting charged. Okay. So let me quickly write. So bending formula. So bending formula. So this was M is equal to EI kappa. Kappa is the curvature, or we can also say that EI by R. So we know that M is bending moment. EI is bending stiffness. And EI. And R is, and kappa or R, you can say that kappa is bending curvature, which is 1 by R also, 1 over radius of curvature. So the formula for kappa, if you see, that is d square by o dx square, because curvature is always related to the second order derivative, and it has first order derivative also. So this is the exact formula d for 3 by 2. But when we have, let's say, your dy by dx, capital X I'm saying, because there's all the assumptions have been discussed in the lectures, but small x is the x coordinate of the current configuration, and I mean the deformed configuration, and capital X is the x coordinate of undeformed configuration. And we say that we assume that there is not much change in x coordinate of current and undeformed configuration. So that's why this capital X, we replace this small x with capital X. So also we say that the slope of the beam is zero, and this is true for many kind of beams that you see. So let's say you have your house, okay, or some stadium, and that is made of fiber reinforced. I mean, steel bars are reinforced in concrete, and if you see the deflection of those steel bars, so that will be very small. So slope will also be very small. Okay, so in structural elements, the slope of the beams are very small. So we can assume the slope to be smaller compared to curvature. So that's why we are neglecting the square of the square will be further smaller. That's why we are neglecting the square of the slope of the beam. Okay, it's valid for many structural beams because those are very stiff beams and they do not undergo much large slope variation. I mean, much large slopes. They are not subjected to much larger slopes. Before that only they will fail. Okay. So anyway, so let me just quickly write. So this is a acceptable assumption. So then your kappa becomes a function of x, and this becomes, I mean, del square over del. I'm just writing partial derivative here, um, not full derivative. Because y would be anyway. Let me just write partial derivatives of del square y over del x. Here, y could be function of any other coordinate z also. But here we are dealing with only x. So kappa x will approximately be equal to, this will approximately be equal to del square y over del x square. Okay. So then you have this formula L eid square y over dx square. Because kappa we have put d square y over dx square. So if you put in the original formula, so that will be eid square y over dx square will be m. Will be equal to m. And m can vary with x. This is the final formula for Euler-Bernoulli beam theory. Then we have Timoshenko beam theory. So in Timoshenko beam theory, so that is valid for relatively thick beams. So in thick beams, the cross section is not perpendicular to the central line after deformation. So we are here we have two constants. One is the deformation of the central line, and the other unknown is, so we two unknowns. One is deformation of central line, other unknown is the rotation of the cross section. Okay, so we have Timoshenko beam theory. So formula, I'm just writing the formula. You can refer to the lectures if you want to see detailed derivation. This formula will be varied. Ei kappa is equal to m. So, but here now we do not have kappa is equal to del square y over del x square. So we do not have that. Okay. So in this case, there will be two equations. One equation will be dy by dx minus theta will be equal to v over k times. So k is shear correction factor, and G is the shear modulus of elasticity, A is area of cross section. So this equation will be to find theta, which is orientation of cross section with respect to central line of the beam, and this will be the second equation, EI d theta by dx. That is it. So first equation will be to find out this deformation of the central line of the beam, and second equation will be to find out theta. I mean, these two are coupled equations, but there are two equations and two unknowns because y is also not unknown, theta is also unknown. So then we have at the last buckling of columns also been discussed in the lecture. So I'm just writing the formulas, buckling of columns. So that is, so critical buckling load was pi square EI over 4L square. So it was for a particular kind of boundary condition. You can just see what kind of boundary condition was there in the lectures. So L was length of the column here. So it's not a general formula, it's for particular boundary condition. Please refer to please refer to so it's I'm just writing this formula is corresponding to particular boundary condition. And if I am right, it was corresponding to one end fixed and one end free. Yeah. Boundary condition, one end fixed and one end free, other end free. For the column. So for different boundary conditions, you have different formulas. So actually, generalized formula is this one: pi square EI over LE square. LE square. LE is the effective length. So here, this is not length, but it is effective length that is calculated based on different boundary conditions. Anyway, so for fixed free boundary condition is 2L. You can just refer to books to understand why it is 2L. Anyway, so let me just give you some questions. So one question will be corresponding to Euler-Bernoulli beam, other will be corresponding to Timoshenko beam. So let me write this question corresponding to Euler-Bernoulli beam. So question is, suppose a beam is kept with a roller support at one end, that is at x equal to 0, constrained to only move in y direction, and pinned at the other. And it is pinned at the other end. Other end is at x equal to L, as shown in figure. I'll draw the figure. So it is also given that beam is subjected to transverse load which is P at the middle of the beam. have to find the deflection of the beam using Euler-Bernoulli beam theory. Okay, so let me draw the figure. So beam is like this. This is the fixed end of the beam. And let me say that there is a rotor support here. So this is y coordinate, x coordinate, and this is P, and this is L by 2. And this is L. Okay. And here it is, here there is no deflection is allowed here, but bending is allowed. So boundary conditions are like at x equal to 0, your deflection is 0. Sorry, you can have deflection, but your so it is allowed to move in y direction. So here slope of the beam will be 0. And here the deflection of the beam will be 0. And you need two boundary conditions because it is a second order differential equation. This one Euler-Bernoulli beam theory has a second order differential equation. So you need, so if you integrate it twice, you will get two integration constants. Those two integration constants will get characterized using these two boundary conditions. Okay. So here you have slope of the beam as 0 because it can move in y direction, uh, but it cannot have a rotation. So it's kind of a fixed beam here. So if you bend it, so slope here will be almost 0 horizontally. On the other hand, at the other end, it can bend. So slope will not be 0, but deflection will be 0. Anyway, so let me do the solution. If I draw the beam, so let's say um this is point A and this is point B. So let's say the bonding moment acting at point A is this, in this direction, and load already we know that so this is at the center P, and this is at a distance of L by 2. So at point B, due to this support, there will be some reaction. I'm calling that reaction as RB. Okay, let's this reaction be RB. So if you balance the force along y direction, so let's say you do sigma Fy. So you have taken the positive direction to be upward direction, negative to be downward direction here. So sigma Fy, if we do, so you'll get a reaction force plus this vertical force P, and there's no other force, so that should be equal to 0 because this is in static equilibrium. Beam is in static equilibrium, so RB will be equal to minus P. It means at RB you will have force like this, acting in downward direction. Okay. Now let's find out MA. So if you balance So we say that in this case upward is positive, and on the positive face for the moments we have taken the convention that on the positive face, if we have a moment in anti-clockwise direction, that is positive. So that's why let's say we balance moment about the central point of the left end. So I'm just writing moment balance about left end. So that will be equal, that should be equal to 0. It means at left end you have minus ma, because I mean this will be going in minus z direction, okay? Because if you apply right hand thumb rule, it will be going in minus z direction, and we have taken plus z direction to be positive, because if you apply this rule, so plus z direction is positive direction. So that's why this will be minus ma, and this load P which has been applied, this will be in plus z direction because we are balancing about this point here. So doing moment balance about this point, central point of the left hand cross section. So if you do that, so you'll get plus of PL by 2 and minus of this due to reaction which is in downward direction, so that will be minus of PL. That should be equal to 0. So if we calculate, finally you'll get MA is equal to minus of PL by 2. Okay. And using Euler-Bernoulli beam, so now you have the value of Ma, that is moment acting at point A. So now you have all the reactions. First, you have to find all the reactions and the reactive forces and reactive moments that we have done. Now we will apply Euler-Bernoulli beam theory, and then we'll find the deflection of the beam. So let me just write. So using Euler-Bernoulli beam theory. So we have EI d square y over dx square, that should be equal to moment. And you know that if you try to find out the moment here, so up to this point, moment will be like p into x. If we consider x from p into l minus x, is if we consider x from this end, so it will be p into l minus x. But suddenly here there is a point load, so moment will change suddenly up to this point. So that's why we will solve this problem in two parts. One when x is ranging from 0 to l by 2, and then other part will be x when x will be ranging from l by 2 to l. Okay, because this moment m will change suddenly at this point l by 2. Okay, that will not be continuous, that will be sudden change. So that's why we want to solve it in two parts. Then at this point we will enforce continuity conditions that at this point of the beam, at this x is equal to l by 2, we have deflection coming from the left hand solution should be equal to deflection coming from the right hand solution. Also, slope coming from the left hand solution should be equal to slope coming from the right hand solution. So these two constraints we will put, and then we will finally solve. But we are going to solve it independently first, for the left part and for the right part, because this value of m is going to change suddenly. So that's why the solution of this differential equation is going to change for the left part and for the right part. Okay, so let me do that. So we just write. So here mx will be cross section will have different expression for x less than L by 2 and x greater than or equal to L by 2. So we consider two cases separately. So firstly, let's suppose that for x greater than or equal to L by 2, I'm just drawing the free body diagram of the beam. So we are starting from this will be the beam, and let's say this is, and let's say this is at a distance x from here. Okay, and this L by 2 is here. So this is P, which is acting in the distance of L by 2 from the left hand. So this is point A, this is, and this is here. RB is acting. So instead of RB, I'm writing that at this point, P is acting in downward direction that we have already found out. And this is point B. Okay. So, and here also MV is acting. Now, if you balance the, now if you draw the, this cross section here, this cross section, so P is acting at this point, and let's say on the negative face, a positive shear force will act in negative direction. So that's a sign convention that we are following, and movement will be in this direction. Let's say mx on this cross section here, this cross section. Okay, and for that, if we balance the force, we balance the force in y direction, so we will get, if we balance the force, so we'll get Vx is equal to minus of P, because Vx and P are in opposite directions. And if we balance the moment about this point at the center of this element to the left hand side, so finally this mx will be when you, so this is actually positive bending moment. Bending moment means it will be, if we talk about stresses, so this will contribute to positive, this will contribute to same kind of stresses that this kind of movement here on this face is going to contribute, because stresses depend on face, and stress is a tensor, it's going to depend on face normal as well as the direction of the traction. Okay, so but when we are doing equilibrium, when we are writing equilibrium equation, we will treat this as um, external movement, not bending moment. So bending moment is used to calculate stresses. It has separate sign convention, and when we write equilibrium equations or force and moment balance, so this is treated as external moment, which has a different sign convention. Its sign convention is simple, that if it is in positive x direction, it is positive. It is in negative x, sorry, if it is in positive z direction, it is positive. If it is in negative z direction, it is negative. So here it is in negative z direction. So we will start with this. So it is minus mx minus of p into L minus x. That will be equal to 0. So mx here is equal to minus of p into L minus x. So if I write and 4x less than L by 2, 4x less than L by 2, if we draw, so that is x, and that is moment ma, and this is p, which is acting at a distance of L by 2, and this is p also acting here. Okay, and if I draw this section now, so this section, he will be acting here, he will be acting here. Let's say v of x is acting here, and mx is acting here. If you do the force and moment balance, so finally v of x is going to be 0, because p and minus p will get cancelled. If you do moment balance, so it will be, moment balance will be minus of mx plus p into L by 2 minus x, right? And minus of p into L minus x equal to 0. So if you find it out, so your mx should be equal to minus of pl by 2, which is constant quantity. Constant because not very, here it was a function of x, but here from 0 to L by 2, it is, it's not a function of x, it's a constant. Okay, so and then we have boundary condition. So boundary condition 1, which is valid for x less than L by 2. So slope at x is equal to 0 is 0. So this implies that if you find dy by dx corresponding to x equal to 0 is 0, and the second boundary condition will correspond to x greater than L by 2, greater than equal to L by 2, let's say. So that will be displacement at x is equal to L is 0. So it means your y at x is equal to L will be 0. Okay. So if we solve now, if we solve for x less than L by 2, let's say, so you have EI d square y over dx square is equal to mx. And now if you put the value of m, so you'll get EI d square y over dx square, and which is minus of PL by 2. It's not a function of x. Now if you integrate once, so you'll get dy by dx will be equal to minus of PL by 2 into x plus c1. And if you satisfy boundary condition that at x equal to 0, x equal to 0, your dy by dx will be 0. So if you put x equal to 0 here, dy by dx equal to 0, it means your c1 will be 0, right? Because this term will vanish at x equal to 0. So so using so this was using boundary condition 1. You'll get c1 as 0. So finally you'll get EI d square y over dx. Sorry. Finally you'll get dy by dx is equal to minus PL by 2 into x. Now if you integrate once more, so you get y is equal to, obviously EI I have not written here, EI will also be there. So y will be equal to minus of PLx square by 4 EI plus C2. Okay, and we don't have any boundary condition yet for finding the C2. So now for x greater than equal to L by 2, we have mx, we have found above that mx is minus of p into L minus x, right? So we have EI d square y over dx square, which is minus of p into L minus x. Now, if you integrate it, if you integrate this equation twice, so finally, I'm just writing the final expression. If you integrate this expression twice, you will get 1 over EI minus of PL x square by 2 plus px cube by 6. Please do it with your own hands. Plus d1x plus d2. And why I have gone up to displacement? Because I have displacement boundary condition. So I have been given that pi at x equal to L is equal to 0. So that was boundary condition 2, right? So if you put x equal to L in this expression and equate the left hand side equal to 0, so finally what you will get is um, you will get a relationship between d1 and d2. Sorry, you will get d2 actually, because at x equal to 0, all these three terms will disappear. Only you will be left with d2. So d2 will be 0, right? So in this equation, you are left with d1 because d2 you already found out, and in this equation you are left with c2, right? So you have two more unknowns. So these two unknowns will be found out by using continuity condition that I was discussing. So at the interface, that is at x is equal to L by 2, what will happen? Y coming from x is equal to left hand side solution L by 2 minus. That should be equal to y coming from x equal to L by 2 plus. So and there is a slope continuity also. Similarly, dy by dx coming from x equal to L by 2 minus should be equal to dy by dx x equal to L by 2 plus. So if you put these two conditions, so finally, so you don't have to do anything. You just take this formula here. You have to put x equal to L by 2, and here you put x equal to L by 2. Equate both these formulas. You'll get some relation between d1, sorry, d2 and c2. Sorry, d1 and c2. Yeah, d1 and c2 because d2 is 0. And then you differentiate this equation and you differentiate this equation also. So if you differentiate this, this will go to 0, and put x is equal to L by 2 here also, here also. And if you equate these two expressions, you will get the value of d1 there. And from this value of d1, if you substitute the value of d1 in the previous equation, which was found out using this expression, then you will get the value of c2 as well. Okay, that's how you will get. Finally, I'm just writing the value of d2 and c2. So d2 you should get as 5/24 PL cube, and c2 you should get as. So these kind of questions may be asked in the exam as well. So please try to solve this completely. I'm just writing. I've told you the procedure and I'm just writing the solution, final answer. And now I'll also tell you how to solve Timoshenko beam question, because it has two differential equations which are coupled. So uh, finally the solution, you will get two solution here. So yx will be equal to minus of PLx square over 4EI plus 11 PL cube over 48 EI. And this is valid for x less than L by 2. And this is 1 over EI. And then this is minus of PLx square by 2 plus P x cube by 6 plus PL square x by 8 plus 5 PL cube by 24. Not working. And this is valid for x greater than equal to L by 2. This is the final solution. Now let's say we have another beam problem, which is something like this. So now this is different color. So you have to follow the similar procedure. Only thing is, I just want the boundary conditions to be different. That's why you have this problem. So you have this roller here. We enlarge the rollers. This roller will be touching the supports. Okay. So this is a beam, and here you have the support as fixed. So, and here a load is applied. So this distance is L by 2. This distance is also L by 2. And the boundary conditions are, this is point A, this is point B. The boundary conditions will be, so at point A you have been allowed deflection. So at point B, what will be the boundary condition? So boundary condition will be, so you have to solve it using Timoshenko beam theory. So that's why theta x will be 0 here. There is bending of the, I mean, the cross-sectional plane will remain attached to the support. It's not going to change angle. So plane normal will be 0 degree. So and also you have theta at x equal to L, you can say. Let's say I start with x equal to 0 from this side. So theta at x equal to 0. I'm starting from this side. So this is my coordinate system. So this is x coordinate, this is y coordinate. So at x equal to 0 will be 0, and y at x equal to 0 should also be 0. And here you have y is allowed. I mean, the movement is allowed, but let me see. Boundary conditions. Y of 0 is 0. dy by dx, d theta by dx at 0 is 0. Sorry, theta will be 0, not d theta by dx. Theta will be 0. And then theta at L will be 0. Okay. So here you have theta x equal to L. So that will be 0. But here it can move above and below, so deflection is allowed. Okay. So let's say the force is P again here. So you have to follow a similar procedure as done in the previous question. Only thing is you have to apply. So you have to solve this question in two parts. Again, at the center point, you have to enforce continuity condition that theta coming from the left hand side solution and right hand side solution should be equal. Also, y coming from left hand side solution and right hand side solution should be equal. Okay, and you have to apply boundary conditions also to know the value of constraints after integration. So let me just give you a brief idea. So I'm not drawing other diagrams. I'm just writing the solution. You try to solve it, and if you're stuck somewhere, you just write in YouTube comment box, and I will upload the whole solution. Okay. If you face any problem, let me write the solution. I'll give you a sufficient hint so that you are able to do. So let's say for x uh, less than L by 2, y of 0, I mean x equal to 0 will be 0, and beta x equal to 0 will be 0. These are the boundary conditions, so we can say that this is C1 and this is boundary condition 2. For x greater than equal to L by 2, you have theta at x equal to L. So that is 0. Now you have two equations. So if you go for x, you can find the bending moment for x equal to L. You can take your own convention. So there are two conventions. One is for bending moment and one is for moment. So when we write the equilibrium equations or when we balance the moment and forces, we treat that as moment, external moment, kind of external moment, but it is internal. And when we write the stresses, we treat it as bending moment. And similar with the shear force. So shear force, when we write in stresses, so we then say that shear force acting on a positive x space in positive y direction will be positive, and on negative x space in negative y direction will be positive. Whereas if you write the uh, force balance, so it will be similarly, it will be simply, if you have a shear force along positive y direction, it will be positive, and if you have shear force along negative y direction, it will be negative. There will not be any role of phase, any phase. Okay, so only in the calculation of stresses the phases come, because stress is a tensor. It involves, it should contain, it contains the information of phase normals. Anyway, so for x less than L by 2, if you find the moment, so uh, and you please take this sign convention only, I mean this coordinate system only, x going from 0 to L by 2 here and L by 2 to L here. Okay, so for x less than L by 2, if you find mx, so that will come out to be um, so that will be ma moment at point A minus p into L by 2 minus x. Okay, and your v of x will come out to be minus of p for x less than L by 2. For x greater than L by 2, your mx will be equal to MA. MA will be unknown here, you won't be able to find out. And your Vx will be 0. I mean, MA is unknown, but you will be able to find out later on. As of now, it is unknown. So now you have, so this is for x greater than L by 2, greater than equal to, you can write it here. Okay, so let me draw the diagram here also. If you have this beam, this point A, this point B, this is load. Actually, it is not P, it is P by 2. So P by 2 here. Yeah. So MA will act here. MB will act here. P by 2 will act at L by 2. And here you have RB. So RB, you are able to imagine that it should be P by 2, right? Why it's saying P by 2, it should be P2. Sorry, yeah, it is P, not P by 2. Just take P. Okay. So you can find out RB initially. So I think no, RB will also be unknown, I think. Let me just see. In this case, if you balance, so there will be reaction. Okay, since A is free to move, there will not be any reaction on A. So RB will be equal to P. Okay. So since A is free, sorry, A is A can have translation, okay, translation in y direction. So there will not be reaction in y direction. So RA will be 0. I mean, there will not be any reaction at A. RB will be equal to P. And obviously that will be in upward direction only. So that is equal to P if you try to find it out. And we say that RA will be 0. Anyway, so now there are two equations for Timoshenko beam theory, which is EI d theta by dx, that is equal to mx. And then you have dy by dx minus theta x is equal to u of x. So in each, so let's for each x less than L by 2 and x greater than L by 2, you have mx and vx. What you are going to do is, firstly you are going to solve this equation. You will put the expression for mx, integrate it. You will integrate once, you will get one integration constant, right? And if there are some bounding condition, put that, characterize that constant. Okay, and then put the value of theta here. So once you put the value of theta here, you already know the value of u of x in that cross section, or in that part. Let's say x less than L by 2 or x greater than L by 2. And you all now you have theta from this equation. So you solve for dy by dx. Firstly, you have to solve this equation, then you have to solve this equation. From this equation, you'll get expression of theta. From this equation, you'll get very expression for y. Okay, and at the end, what you have to do is there will be some unknown values. So that those unknown values will be you can find using the continuity condition of slope and displacement at x equal to L by 2. So at x equal to L by 2, you have y coming from left hand side and y coming from right hand side should be equal, and theta coming from left hand side and theta coming from right hand side should be equal. So finally, if you do all these things, so you should obtain this solution. You should obtain that deflection at A. So y at A. So that should be equal to minus of PL cube over 24 EI, and this is minus of PL over 2 of kappa GA, and then MA will you will also get MA, you will get PL over 8. Okay, so this is the final answer that you should get. And if you're not able to get it, please write to me. You can comment on the uploaded video on YouTube. so you can write a comment. Okay. Okay, so we'll stop here for today. Thank you all of you for your attention.